Hello, everybody. My name is Mohammad Zah Sharif. Today, I would like to talk in a new YouTube video, explain about the Fourier transform and convolution integral. The convolution integral, how we can define, suppose that we have a signal xt. This signal is one-dimensional. So for instance, this signal can be any in time domain, any signal of audio or radio frequency, whatever. It depends on the frequency. And that this signal, for instance, passing through a channel to a filter with the impulse response of ht, and the output will be the convolution between these two. The convolution integral is defined by this equation, which with a tau, another variable here. The integral is xt, ht minus tau, and theta. The ht is the impulse response. Ht is the impulse response of the filter. This filter, for instance, xt is passing to ht. This signal is passing to ht, and we get the output yt. This channel, this filter could be any filter, digital filter, or any what kind of filter with the impulse response of ht. And what is the impulse response of ht? If you insert the delta t, the Dirac delta function, which is defined by this equation, is at t0 is infinite, at t not equal to 0 is 0, then this is the impulse response ht defined by the delta function, Dirac delta. And then is this. Well, this signal, suppose that we're starting from the minus infinite to plus infinite. And then in the next slide, I will show the Fourier transform of this. The Fourier transform is defined by this formula, yt e minus j omega t dt. So the time domain converted to omega, which is frequency domain, with the using the Euler function, the Euler formula, then yt will be sine of, for instance, in simple cases, sine omega 0, this one, and then the Fourier transform will be calculated like this. As you can see here, in the frequency domain, it's shifted a little bit, sorry. We have two impulses, one at minus omega 0, one at plus omega 0. This is to go to infinite and minus infinite. This is the our signal with the frequency omega 0, and starting from minus infinite to plus infinite. Anyway, the impulse, the Fourier transform will be two impulses like this. Now, today I want to emphasize for the case that our signal is finite, because no phenomenon in the world is not from minus infinite to plus infinite. For instance, it's starting from at 0 and ending at after n cycle with the simple case of sine or cosine wave like this. Sorry, it's shifted a little bit. Sine omega 0 is like this, cosine omega 0 is like this. This is time domain. Anyway, our signal is yt is ej omega 0 t with the frequency omega 0. And what is important here is t starting 0 and ending after n cycles. So in this case, no more the Fourier transform of this signal anyway, or this signal will not be just like the previous I show you. It's not like two impulses like this and this, because the final length of the signal starting from this 0 to n cycle, nt0, then if the signal is this, then let's start to find the Fourier transform of this finite length signal. This is our main point in this video. The Fourier transform of this finite length with the n is nt0 from starting from 0. So our integral is not from infinity to plus infinity, minus infinity to plus infinity, but from 0 from nt0. And then by Fourier transform, so our Fourier transform of the signal will be like this, and calculation like this, and making the integration like this, then we obtain such a signal like this. You can do it by yourself anyway. Uh, so this is our Fourier transform, in this case, a special case of finite lengths. And we can also rewrite it with this, just factorizing this part, so it will become like this, using the Euler sine omega is e j omega minus e minus j omega over 2j. Using this formula, this formula will be like this. This is sine something over that, sine x over x, for instance. This is, we call it sinc function. So our new Fourier transform of the finite length has a phase like this, and the amplitude with the multiplication of the sinc function. Let's start like this. The sinc function is defined like sine x over x, which is, we call it sinc x. And this x is the same x as this, anyway. And so we can rewrite y omega as this one with the sinc function, just very simple sinc function. I show you an example. For instance, we have omega 0 with 2 pi omega 0, and omega 0 is 4,000 hertz, for instance, audio signal 4,000, or can be any signal, with the period of the 1 over 4,000 second, and n is only 10 cycle. So it's a finite length. Now we want to show what is the finite length Fourier transform. In the next slide, I will show you the graph of the sinc x by using from alpha, this one. So in the case of the f0 4000 and so on, the sinc function, it becomes like this, not only one impulse, rather it has one main lobe and many side lobe until the maybe infinite, but gradually decaying. So why it is like this? Because it's like sinc function. This graph is, we use this all from alpha to graph it. We can use it MATLAB or other. Okay, next slide. Now we would like to show the relation between the time domain and frequency domain, or convolution and Fourier transform. Suppose we have a signal xt passing through the filter ht again. Then the output will be yt. As we have defined the convolution integral, now this is the relation is the convolution integral. Now we convert this to the frequency domain. Frequency domain. What is the relation in the frequency domain? This is our question. So let's have Fourier transform, define Fourier transform as we explained before for you. Xt, the Fourier transform of xt is x omega. Ht, the impulse response of the channel or filter, is h omega, and Fourier transform of the output yt is y omega. Now, we can write that the y omega, the Fourier transform of the output, is multiplications of the input frequency domain and the impulse response frequency domain. This is very important because this multiplication is performed in each frequency being. I mean, each frequency is multiplied and find the new magnitude and phase in the frequency domain, rather than convolution, which is very complicated uh, calculation. So the number of the, in this case, using the frequency domain, the number of the computation in the frequency domain will be very smaller than computation number in the, for instance, for using convolution in the time domain, because the convolution in the time domain is yt is xt, asteristic ht is separated. This is it should be separated. So yt can be written like this. This computation is rather complicated because it needs much more computation number, as for instance, because for finding hyt. But if you use this one, it's very simple. Just transform to the frequency domain, multiply, and invert, reverse back to the time domain. That is saving in computational number. But for the final length signal, of course, like this, the signal, we may have the circular convolution, which is not good because it's not a linear convolution. That should be compensated by zero padding and half overlap save, or half overlap save or add method, which is the topics for the next video. And this is what I wanted to tell you, the finding the Fourier transform of the finite length signal and relation between the frequency domain and time domain. And thank you for your patience and listening to this video. Thank again, and I welcome your comments, and you can see my other channel in this this URL, and then I will stop here, and thank you very much. That's all, very simple. Thank you very much. I'll stop here.